In addition to mastering all of the one-step problem types, second graders also gain skill with many of the two-step problems. This aspect of the curriculum is rife with both challenge and opportunity. As teachers, we know that it really will be a challenge to get all of the students at a point where they can solve a number of these two-step problems confidently and independently for the assessment. But on the other hand, it is actually through developing this skill that we see the greatest intellectual development in our learners. Before we go into two-step problems, we need to sort of step back and recall some things about one-step problem difficulty, and that's going to become obvious why we need to do that in just a moment. So remember that one-step problems are classified into easy difficulty, easy level, medium difficulty, and then very difficult. The easy ones were first introduced way back in kindergarten. They should be a pretty familiar scenario set up for the students, and they've continued to work with them with larger number sets. The medium ones were first introduced in first grade. They're the change unknown and some of the easier compare problems with no misleading language. And those are not as solid, obviously, as the easy ones, but they may still be used for two-step. The difficult problems, not all first graders master those. That's actually on our docket or our to-do list for second grade, is to get those start unknowns and the compare problems that have the misleading language. All right, so why is it so important that we know that? Well, two-step problems are essentially constructed by combining two of the one-step problems. And whatever the difficulty of the one-step problems are, that's going to influence the difficulty of the two-step problems. So we need to really be aware of that difficulty as we assign or construct our own two-step problems for students. Another issue that we also need to be aware of, and this is mentioned here in the Common Core progressions as well, and that is that students who have not yet mastered a particular problem type as a one-step, that problem type is not very useful for a two-step, and then especially the difficult problems. The difficult problems are not appropriate for being merged into a two-step problem because many second graders are still developing mastery of those areas. The Common Core authors also encouragingly tell us that we don't have to have them doing the two-step problems with really large numbers. The students who struggle can learn to do these problems with small number sets, and that will be acceptable. So by combining different difficulties of one-step problems, we end up with 5 different levels of difficulty for two-step problems. Second graders are expected to reach mastery through level 3. Level 4 difficulty could be appropriate for your most advanced learners as a way to keep them challenged. Level 5 is not considered appropriate for second graders. Each of these difficulty levels, we'll now go through them individually so you can see how they work. Level 1 difficulty is characterized by combining 2 easy problems with the same operation. So in the example that you see here, we essentially have combined 2 result unknown problems, both of which require subtraction. Children are expected also to be able to identify a matching equation for this problem type. When you combine 2 easy problems, usually the children can come up with an equation. Now, that doesn't mean they can do it at the beginning of the year. It is a process that we want them to get to by the end of the year, so we work with modeling, scaffolding, guided practice with feedback before we feel like we have to do any formal assessment. Level 2 difficulty is also formed by combining 2 easy problems. But in this case, instead of having the same operation for both, they're opposite operations. So we can combine 2 problems. In the example you see here, the first problem is actually a result unknown where we have to subtract, and the second one is a result unknown where we have to add. Again, students, it's a little harder, but students should be able to come up with a matching equation for this kind of problem by the end of the school year. Level 3 difficulty, this is still a problem. This is the most difficult that you need to try to get all of your learners to accomplish. So this is the target goal. is the level 3. And level 3 definitely ups the ante on the difficulty. It's going to be very difficult for them to come up with a matching equation, and the Common Core authors in their progressions document indicate that they don't have to come up with one matching equation. It is quite acceptable for them to be able to do the problem in chunks, as I have shown here at the bottom of the page. That's totally okay, according to the Common Core authors. Because the difficulty level is considerably higher, because we've now introduced a medium in the mix along with an easy, models become incredibly important here in order to keep track of what's going on in a problem. Problems of level 4 difficulty are just for your most advanced learners. Children will need some really good modeling skills in order to be successful, because the relationships, the mathematical relationships, are harder to pull out of these problems. They combine two medium difficulty problems. So I have an example here. At any point in time, pause the presentation so you can spend more time studying the problems and the models at your own convenience. You'll notice that the matching equation would be very difficult for a child to write on their own. So again, they'd probably be doing it in chunks. When a class or group is working on mastering problems with a new difficulty level, try to manage their cognitive load on just that new difficult thing, and then take all of the other aspects and make them as straightforward as possible. So use low number sets, perhaps a lot lower than they're used to working with, so they feel like really comfortable numbers to work with. They also will likely experience some strategy setbacks. That's normal. So in other words, you see a child doing mental math and some cool things, you give them a difficult problem and they're counting on their fingers. That is normal. It is a sign that they are really stretching their problem-solving skills, and their cognitive load is being used up on the new difficulty. So don't be alarmed if you occasionally see, when you give them a hard problem, that strategies and other things appear to be falling by the wayside. When they master the new problem, then you can work those more advanced strategies back in. Children do not necessarily proceed in a linear sequential fashion quite as neatly as this chart might lead you to believe, but this is a sort of general idea of how you can think about mastery of problem types over time during the second grade year, although this actually starts before second grade. Each of the easier problem types than what you're working on can continue to be part of your curriculum, but usually you're using those for perhaps getting them comfortable with working on strategies for large numbers or place value. One thing that is clear in this chart, though, is that second graders do not have to wait to have mastered all of the one-step problems before two-step problems are introduced. So even though they may still be struggling with difficult problems, you can still give them two-step problems that are composed of two easy problems, for example. That would be perfectly acceptable. In our work with young problem solvers, it often seems as if some children are just born good problem solvers and others aren't. However, good problem solvers really can be developed. It doesn't have to be a matter of winning a genetic lottery. Growing strong problem solvers requires intentional scaffolds to foster these skills. So what kind of things can we do to develop good problem solvers over time? Well, first we need to be explicit in supporting learners how to model the problems, because a failure in modeling often causes children to miss certain important mathematical relationships. And so we're going to have to model both diagrams and equations. Our ultimate focus is on fostering children's meaning-making skills. Just because I draw a model or tell a student how to draw a model doesn't mean that that model will be instantly useful to the learner. We need to ask a lot of questions, such as, suppose that I draw bars to represent Sally's and George's money. Which bar should I make longer? What are you noticing in the word problem that makes you think so? So those are the kinds of things that happen during the modeling that draw students' attention in and focus their attention on some details. And I have another example here as well. Off to the left, you see I'm explicitly drawing children's attention to how I'm demonstrating a mathematical relationship with the bars. And then I can ask them what these numbers and bars mean in terms of the actual problem that we're working on. I can also show a model incorrectly drawn, as you see off to the right, and ask the students, critique this model. Tell me how to fix it and make it so it will work. Through these kinds of discussions, the learners come to understand for themselves why the models have to be lined up along one edge in order for them to work, or where is the difference in the model. They come to see these things, and the model grows in its usefulness over time. Have you ever had a student who made a lot of errors simply because they didn't carefully read the problem? We can set up learning experiences in which students must actively develop their capacity to be deep noticers, deep observers. And to accomplish this goal, we have to plunge them into a situation in which the only way that they're going to do it is through careful reading. So there's an example of that here. By providing students with a set of similarly worded problems, but all of them have different problem types, we can really develop those noticing skills. In this case, the problems all involve the same context, the same people, and the same numbers. I've shown the models that go with each of these problems here. However, when I do this with children, and I would never do this till they're comfortable with how the models are constructed, but once they get comfortable with that, I would give them these 3 problems and these 3 models and have them figure out which model goes with which problem and what makes you think so. What are you noticing? Defend your position. You're really getting at some mathematical standards of practice here too, because you're looking at building in some reasoning. They have to pull meaning out of the words. They have to model with the mathematics. They have to critique the reasoning of others. You're getting at mathematical standards of practice 2, 3, and 4. Children, like most people, will often choose the path of least resistance. If there's a way about going around something that involves less work, then that's going to seem attractive. And this can play out in math classrooms with some really negative consequences. One of the ways in which that happens is that learners will often pull numbers out of a word problem and just slap an operation sign between them. To figure out which operation to use, they often use superficial clue words and/or, well, we've been studying subtraction lately, let's use a subtraction sign. This is really problematic in terms of preparing the students for future mathematics learning and also preparing them for the standardized test, because there's really anything is fair game on that test. It's not going to be whatever's been studied most recently. Therefore, we need to ensure that students are accustomed to seeing enough variety of problems, that they recognize the need to always be careful readers of problems, not just when the wording of 2 problems is similar, but in all cases. So we're going to take a look at a math assignment. This comes from mid-2nd grade in the primary math series. Number 1 through 10 are not here. You don't see them. They actually were just working on recent target skills. And then it goes into the word problem section. I have off to the right in that column, I've actually shown you whether it would be classified as easy, medium, or difficult, whether it's a 1-step or 2-step, and what the problem type is. And you'll see a lot of variety. There's 2 easy, 2 medium, 2 difficult. They are all 1-step problems, but they're still preparatory for 2 steps because of the fact that the students are developing these skills to be close readers who can really pull the details out and study them. If they can shift back and forth between these different problem types, that's going to really put them in a good position for the 2-step problems. You don't want their default mode to be just, well, slap this operation sign, because it kind of feels like might be addition here. You want them to really have some deep skill sets in terms of comprehending word problems. Research shows that students who are most likely to pull numbers out and immediately start operating on them are actually our poorest problem solvers. It seems ironic that the people who get started on the problem solving first are usually the weakest. The strong problem solvers are slower. They take more time to read a problem carefully, to understand the mathematical relationships. They often take time to draw a diagram to help them make sense. They make decisions about what strategy to use and why would that strategy be helpful in this situation. So it's helpful to develop some class-wide guidelines about solving problems, and those guidelines will often involve slowing students down to take time to make sense before they plunge into trying to do something with the numbers. Teachers and students could often refer to a set of guidelines which you have posted in your room. They could refer to that often, and you could give students feedback on how they're doing in reference to those guidelines. Here's an example. Off to the left, you see sort of a process, an instructional process for how you could introduce the problem-solving process, and then what the follow-through would need to be in order to ensure that students are doing that and developing that area. And then off to the right, you see an example of what a problem-solving process could look like that you and your students might come up with together. This one's very simple. I've seen some that are considerably more detailed, many more steps. But for second grade, I think this is a nice default one, and feel free to adapt that for your own purposes. Our fifth guideline for growing strong problem solvers is to explicitly foster the use of well-known math heuristics. Now, the word heuristics may be new to you. A heuristic is a type of generalized problem-solving technique that can be used to reduce the cognitive load so that you can tackle hard problems. And it's a pretty common word in mathematics circles. One heuristic that we have already discussed is drawing a diagram. Those tape diagrams that we've been using are incredibly useful tools, and they're useful for many different kinds of problems, and they can reduce the cognitive load by making a relationship clearer to us. But they're not the only heuristics that can be useful to your learners. There's actually quite a few of them, and my guess is that these do look familiar to you. The list includes draw a diagram, look for a pattern. The draw diagram we've done already. Make an organized list or a table. Acting out the problem is usually one that feels fairly intuitive to students if they think they're allowed to try that. And write an equation. So think about each of these. These are all things I would expect could be useful to second graders. Are these heuristics developed through your curriculum? Do you see students using them regularly? What would they need in order to come to a point where they would use them more often? Those are some things for you to think about. Keep in mind that the students will only really develop these skills if they perceive the need for developing the skills, which means that you have to give them really problematic tasks where using these heuristics makes the task much easier to handle in order for them to develop that skill. I'm going to stop and just say some quick thing about tape diagrams because you've seen quite a few of them. They are mentioned specifically as a useful tool by Common Core authors. And if you aren't familiar with them, I'm hoping that seeing a lot of different examples will be helpful. Feel free to stop the presentation at any given point in time and study those if that's new to you. I want to talk a little bit about working with students because in second grade I'm starting to try to help train them to design their own models, and some of them don't have the manipulative skills to do this very well. So I have a bunch of cardstock strips of different colors and different lengths that I've laminated, and some of them I put little magnets on so I can use them on whiteboards, but I keep a whole array of different sizes of them in baskets on the table, and students can help themselves to those and use them to set up their own tape model if they do not have the manipulative skills to draw it on their own. One of the things that has probably become obvious to you in this lesson is that problem difficulty can vary tremendously. In order for learners to grow in their capacity to problem solve, we need to be thoughtful about the amount of cognitive load they're managing. So realistically, this might involve giving the same problem to a range of learners, but with different number sets or different wordings to allow the learners to break the problem up into manageable chunks. Giving students different versions of the same problem will allow learners to productively benefit by a strategy share after problem solving. Even though you've differentiated it, they still have enough of a shared experience to come together and have a good dialogue. Here's an example of a differentiated problem that's essentially the exact same problem. The version on the right is easier to do because it overtly splits the problem up into separate parts, and that reduces the cognitive load for learners who can't yet handle the more advanced version. Everyone can participate with essentially the same problem, and yet there can be small modifications for those who find the original problem too challenging. Also, when you introduce two-step problems, you can use a similar process. You can begin with this revised version, and when they get practice with that, then you can shift to the advanced version. I wish you all the best of luck as you work with students in trying to set up two-step problems. This really moves them forward mathematically. Challenge, but